In this lecture, we're going to talk about continuous maps. This is when you have a function between two topological spaces. For review purposes, let's just remind ourselves what it means to be continuous when you have metric spaces. So this is the definition that we had. Let x and y be metric spaces. We're being sloppy here, and we're not writing x comma d, y comma d prime. Like, we're not writing that sort of understood that there is a metric, and we're not emphasizing the metric. So we have two metric spaces. So we say f is continuous at P, at a point. And here, of course, the point is at X. And I forgot to say, and F is a function between these two topological spaces. Now, one can ask, what is the difference between a map versus a function? And actually, there is no difference. You can say you have a function from X to Y, or you can say you have a map from X to Y. There are some people who prefer to reserve the word function when the codomain is like the set of real numbers, or maybe the set of complex numbers. So something that is a number. So a function would then be, it's a mapping that takes a certain set and it assigns values to elements in the set. So there's some people who use that convention, where a function is something that is of a numerical type. It returns to you numbers, but not everyone does that. So some people use the word function and map interchangeably. That's the way we will use it in this course. But I just bring it up because there's some people have this convention that they reserve the word function whenever they talk about evaluating, like actual numbers being assigned by a function. We say the function is continuous at a point would mean that for any epsilon bigger than 0, there is delta bigger than 0, so that if you have something in X and this element is close to the point, so if the distance between X and P is less than delta, then the distance between f of X and f of P is less than epsilon. You will notice I'm also being sloppy here. Like, I did not actually mention the metric anywhere here, and then it just reappears. And then I'm using d over here, and I'm using d over there. I'm using the same d, even though there's really two different d's. But this is part of the sloppiness. You try not to use too much notation. So that's what it means to be continuous at P. And then we would say f, and we say f is continuous if and only if f is continuous at each point. Most of the time, this is what we care about. It's almost never the case that we only want the function to be continuous at just P and nowhere else. And then we had this very important theorem, you can say. We can even call this a theorem because even though it's not super difficult to prove, it's a very important idea. This is the open set restatement. So you would say that f from X to Y is continuous if and only if for any open set U subset of Y, we have that the inverse image of that open set, so that's now a subset of X, is an open subset of X. So we proved this for metric spaces. We proved it one direction, and you had an assignment to prove it the other way. And the way, maybe I should just recall what the inverse image is, and then just recall the inverse image of U, also known as the pullback, is, by definition, that's defined to be points in your set X with the property so that f of X is in U. And the picture that comes along with it is, this is X, this is Y, this is your mapping F, this is something called U, and then you're asking what region is the correct region that goes to that u. So it is all of the points. You see, it's all points in set X, all elements of set X, so that when you apply the function to those points, they end up in that region. So that's the way you can visualize that. That's called the pullback or the inverse image. So that's what it means to be continuous. Now, maybe as an exercise, you may wonder, is there a way to restate this for a single point? Because this is the way you restate it for continuity, but you may wonder that in this original definition, we first talk about a function being continuous at a point. So you may wonder, is there an open set restatement of this by using a single point? And there is a way to do it. So maybe I should just mention it. We're not going to prove it because there's more important things to talk about, but maybe if you're just interested to see it, it makes sense to just write it down. So first, I want to make a definition. So let X be a topological space. We say a subset, let's call it N. So a subset of X is a neighborhood. So we say a subset of X where with with N containing P. So we have a point. The point is in some set, and this is some subset of X. So we say that N is a neighborhood of P if and only if, because this is a definition, there is an open set, let's say U. So there is an open set U. There's an open set. So an open set in X, I should say, there's an open set in X, so that the point belongs to U, and U is a subset of N. So I'm not saying that U is an open subset of N. I'm saying U, you see, this is the reason why I'm writing it like that, to avoid confusion. If I just wrote there's an open set U, you might say, is U an open subset of N, or is U an open subset of X? So by writing it like this, it clarifies the confusion. So that's what we call a neighborhood. If you want an example of a neighborhood, so let's say X is R2 with the usual topology, and P is the origin, so that's the point 0, 0. That's the point at the origin. And N is the closed unit square. And then N is a neighborhood of P. You can see this in the picture. So here's our point P. Well, actually, no, sorry about that. That's not what I meant. Let me change the point. Let me make this point 1/2, 1/2. Sorry about that. That was a mistake. So this is our closed square, and the point P is right here in the middle. It does not have to be in the middle, but it's there. And you can see that you can draw, let's say, like an open disk. It does not have to be an open disk. It also could be an open square or something. But you can find an open set sitting inside N. So an open subset of R2 of your ambient space, open subset of the ambient space, that is also sitting inside this N. So that would be a neighborhood. But N is not a neighborhood of Q, where Q is the origin, because the origin would be located right there. That would be 0, 0. That's the lower corner. And you can see what the problem is here. No matter how small you try to fit an open set, you can never make it be contained within N. Okay, so a neighborhood of a point is a set that is thick enough to contain an open set at that point. So that's what we say, a neighborhood of P. So this is the definition. And now we can reformulate. I'm going to go back to this version. So this is the open set restatement, but you can also do this with closed sets. You can also say that a function is continuous if and only if for any closed set in Y, the inverse image is a closed set in X. So this condition about being continuous at a single point can be also written like this. So let's take this down. Let me rewrite it for you in case you're interested to see how that would go. So you would write it in the following way. Let's write this as a proposition because this is not as important. So let x and y be metric spaces, and f as a mapping from x to y with p and x. So then f is continuous at p if and only if. So this is going to go a little bit differently. Continuity goes like this for a open set in y. Well, here it's all about this point. So the picture here, so let me draw a picture for you. This will make it easier to understand. So the picture here is, this is x, this is y, this is your mapping. You have this point p, and this point gets mapped to f of p. And the idea is that instead of picking an arbitrary subset of y, an arbitrary open subset of y, since you're focused at this point, you're going to pick a subset of y that contains this point. So you're going to pick, now it could be open, but it could be an open, but so you can, if and only if for any, so I think it's better to just use neighborhoods here. So here you're going to draw a neighborhood n. If and only if for any neighborhood n, so this is a neighborhood in y of f of p, so it's something that contains f of p, f inverse of this neighborhood will be a neighborhood of that point, is a neighborhood. Yeah, I really misspelled that, but you get the idea, of p. The reason why we have to use neighborhoods and not open sets, if you're wondering, is like you may be confused, why are we suddenly using neighborhoods and not open sets? Because the reason for this is because in general, if you only have continuity at a single point, and just because you pick an open subset that contains f of p does not guarantee that f inverse of n will be an open subset. That is not guaranteed, because this theorem is specifically in the case where the function is continuous at every single point. So it's not necessarily continuous at every single point. So it may be discontinuous everywhere else, and it might only be continuous at p and nowhere else. So if you pick an open subset that contains f of p, it is not guaranteed that f inverse of that open set will be an open set containing p, but at least it happens to contain an open set that contains p. So that's why we use the language of neighborhoods. So that's kind of what we're saying. So what we're basically saying is, if you want to use open sets, you can kind of say it like this. If you draw an open set around f of p and you pull it back, the pullback may not be an open set, but whatever you get contains an open set that then contains p. So that's it's restated in a slightly more convoluted, more difficult manner. But this is something you can think about how to prove by sort of using this delta epsilon type of a proof. So now we're going to define what it means to be continuous between topological spaces. And this is the common theme throughout mathematics. What used to be a theorem becomes a definition. So this will actually become the definition of continuity. So now we go back to topological spaces and we define what it means to be continuous. So definition. So let x and y be topological spaces. Notice we're not emphasizing their topologies. We're being sloppy like usually people are in math. So let x and y be topological spaces. We say a function between them is continuous if and only if for any, let me write it like this, u element open y. So open y is another way of saying, so x is a topological space, so it consists of x and there's some topology. Y is a topological space, so there's y and some topology. So if you wanted to, you could write something in the topology of y, right? So an open set in y. So you can kind of write that if you want to, but I think it just looks nicer to say for any U element open Y. So open Y, that's the topology of Y. That's the collection of all open sets. So you're picking something in the collection of all open sets. But this just means in the topology of Y. So for any U in the topology of Y, we have that the inverse image of U is something that's open in X. So that is the definition. That's the definition of continuity. And this is actually the reason why we talked about metric spaces before, because if I just gave you the definition, you cannot really appreciate it. But now that you've seen stuff with metric spaces, you can appreciate what's happening more in this definition. You can, of course, do this with closed sets. Maybe I can make a little proposition here. Proposition. This will be an exercise. Maybe, I'm not even sure if we need to make it an exercise because you sort of proved it for metric spaces. So you know what, let's not even make it an exercise because you kind of already proved it for metric spaces. It's the same kind of proof essentially. Proposition, we can replace open by closed in the definition. So in other words, there's basically two definitions, one involving open sets and another one involving closed sets. The two definitions might seem different, but they're equivalent to each other. So if one definition holds, then the other definition holds, and the other way around. So both definitions are equivalent, and you can reformulate everything in terms of closed sets. So that's the definition. I want to give you a warning. So here's a warning. If you have a continuous function, is continuous, then the push forward of an open set does not need to be open. I mean, it could be, but it's not certain. Like, there's no guarantee. So what do we mean by the push forward? So here's what we mean. In other words, if U is an open subset of X, so now we're going in the other direction. Continuity is with pullbacks. So if the pullback of an open set is open. But the push forward version does not work. If U is something that's open in X, then F of U, this is the push forward, is not necessarily open in Y. So what is the push forward? The push forward, this is the set, this is applying F to all of the elements of U. So that would be F of X where X is in set X. I'm sorry, where X is in set U. So that is the push forward. You just apply the function to all of the elements that make up the set. So that's what we call the push forward. If you want to see a picture of the push forward, it's exactly what you think it would be. So if these two squares represent X and Y, and this is your mapping, then if you have some set over here that you call U, the push forward is obtained by, it's also called the image. Sometimes you call it the image because you want to determine, so you're applying F to all of the points in U individually, and they land somewhere like this, and that's what you call F of U. That's called the image. So it's not necessarily open. So let me give you a very easy example. Very simple example. Here's an example. Usually, when you're trying to think of examples, you want to try to think of the simplest possible examples. And if they do not work, you want to try other simple examples. So you can try something with the discrete or indiscrete topologies. Also, it's always a good idea to think about the real numbers because we're used to the real numbers. So in this example, I'm going to use a function from the real numbers to the real numbers with the usual topology. Of course, this is the standard topology. So these are the same topological space. X and Y here are both the same. They're both the real numbers. And the mapping here is F of X is going to be equal to 0. So this is the constant mapping. This is a continuous. So it's easy to see that this is continuous. Now, of course, it's a constant function, and constant functions are continuous. But if you want to see this topologically, here's the way you would see it. I'm going to draw a picture of the real line, and I'm going to draw a picture of the real line again. And our mapping takes the real line to the real line. And let's draw the origin over here, because everything's being mapped to 0. Now look at this. Let's find what the inverse image is. So we're going to draw an open set. So for simplicity, let's draw our open set as an open interval. So if you draw an open interval, and the open interval does not contain the origin, what is the inverse image? What is so this is U. Then the inverse image of U would actually be the empty set, because there's nothing in here that gets mapped to U, because everything, the function is defined by mapping everything to 0. So there's no point in here that gets mapped anywhere in U. So then the inverse image of U is going to be the empty set. But look at that. That's an open set. Remember, empty set is an open set. So if you pick an open interval and your open interval misses the origin, then its inverse image is the empty set, which is open. And if instead your open interval happens to somehow contain the origin, then what points in here land in there? Well, all of them, because everything gets mapped to 0. So every single point, since it's being mapped to 0, ends up in this blue interval. In this case, the inverse image is going to be R. But R, as a subset of R, is also open. So again, the open condition is satisfied. So you can easily see, by thinking this through very carefully, that the constant mapping under this open set condition is a continuous mapping. So you don't even have to use delta epsilons here. You can just see what happens with open sets. So this is a continuous mapping. Now let's see what happens with the forward image. So let's say, okay, so now let's pick, so now we're going to do it the other way around. We're going to look at the forward image, right? The push forward. So what we're saying here is, if you pick something that's open in X, so in the domain, it's not guaranteed that the image is open over here. So let's say we pick U, just to keep it as simple as possible. Let's say U is everything. It's the entire number line. Then f of U, the image of f of U, is just a single point 0. Because all of this entire set, this is an open set, this entire open set, the image, the forward image, the push forward of this open set, when you apply f to all of those points, they end up at 0, right? They all being mapped to 0. And this is not an open subset. This, the singleton point, is not an open subset of R. For the simple reason, because to be an open subset means that you have to be able to fit a disk inside it. You have to be able to fit an open interval inside it, and you're not able to. It's just a single point. So it is not an open subset of R. So you get to see in this very simple example that the push forward does not need to be an open set. Sometimes it could be, but it's not guaranteed. Okay, so I want to mention some propositions. So let's begin with this proposition. Let X and Y be topological spaces, and F is a function from X to Y. Then you would say, so then F is continuous if and only if. This is another way how you can restate continuity. If and only if, for any set A that's a subset of X. Notice we're not saying open, right? We're just saying for any set. Usually, if it's closed, if it's a closed set, we often use like C or K. If it's an open set, we use U or V. Sometimes we use like a script O. And if it's an arbitrary set, then we call it A or B or something like that. So for any set A is a subset. So for any subset of X, we have the following condition, that if you apply F to the closure of A, that is contained in F of A closure. So we have this. We're only going to prove it in one direction. The other direction You can find it in Moncrief's. Again, it's not difficult. It's a proposition. You just have to unravel the definitions. But we're going to prove it. We're going to prove it this way. We're going to prove that if we have a continuous mapping, then f of the closure is contained in the closure of the image. That's what we're going to show. This is the way it would typically be used. Usually when you prove continuity, you never do it like this. You never work with closures, because working with closures is not exactly the most convenient thing to work with. So we usually do not check continuity like that. We generally check continuity if it's metric spaces. We use delta epsilons often. Sometimes we use open sets, sometimes we use closed sets, but we almost never, I've never seen anyone ever check continuity like this. So this is more, the way this proposition is really used in practice, if you ever use it, is in this direction. You would just take advantage of the fact that if you have a continuous mapping, if you want to apply f to the closure, you always know it's going to be contained in the closure of its image. So let's give a proof. So how does it prove this? So here's the way the proof will typically go. So we're going to let Q be a point in f of a closure, and we need to show Q is a point in f of a closure. Okay, that's the way it goes. You pick something on the left and you show what's on the right, right? We're claiming this is a subset of that. So now what is f of a closure by definition? So by definition, f of a closure is equal to, so equal to by definition. So the closure of the set, this is the way we define it. This is the smallest closed set in Y, of course, because f of a is a subset of Y, right? We started with a subset of X. After we apply f to it, it's now a subset of Y. And by the way, there's two different closures over here. This is the closure, of course, with respect to X, because A is a subset of X. And this is the closure with respect to Y, because f of A is a subset of Y. So it's, of course, left to the reader whenever you write something like that to be able to interpret yourself which closure is what. It's whichever one makes sense. So this is the smallest closed set in Y, which contains f of a, which contains f of a. If you want to write it using intersections, you would write it like this. You would say it's the intersection of all closed set C, where C contains f of a, and C is closed. Let me write like this. C is an element of closed Y. I'll write it like this. So C is an element of the closed sets of Y, and C has to contain f of a. So it's the intersection of all of those. So what are we saying? We're saying that Q has to belong to this. So if it belongs to this object, that means Q is in the intersection. So Q has to be in that intersection. So there's this intersection. I'm not going to rewrite everything all over again, but we're saying that this Q belongs to f of a closure. F of a closure is all of this. So Q has to belong to that intersection. Now, if it belongs to an intersection, it means it has to belong to every single closed set. And so Q, so we must show, so to show that something belongs to an intersection, it has to be an element of every single set in the intersection. So we need to argue that Q is an element of C for every C that's closed in Y, and C contains f of a. That's what we have to show. So how do we accomplish this? Well, here's the way we do it. So since Q is an f of a closure, it means, and this is just by definition of image, this is the forward image, the push forward. If something is an f of something, right? Q is an f, so it's f of something. So it means Q can be written as f of something, so f of p, where the p, where the point, is something in a closure. That's what we're saying. Okay, so what do we do next? So here's what we do next. We must show that Q is an element of every single one of these. So now, so we have a closed set, and the closed set contains. So I think this will make it easier. So we must show, right? This is what we must show for every this, and this piece is now being assumed, right? We're assuming this. Q is in here. If you pick a closed set with these properties, we have to show that Q is an element of that closed set. C contains this. So let's rewrite this. So we would say that so now we're assuming this, right? That we have to show this under that assumption. So since C contains f of A, it means, let's use the pullback. It means that f inverse of C will contain f inverse of f of A. Okay, f inverse will contain f inverse of f of A. All we're doing is we're applying f inverse to both sides. That's really what we're doing. So f inverse, well, now f inverse, what is this? This is a closed set. So this is a closed set in X. Okay, so f inverse of C is a closed set in X. Oh, and I should have said one more thing. There's one more thing I forgot to say. F inverse of f of A. Notice you have an f inverse and an f here, so you might think they cancel each other away. But you have to be a little bit careful. They actually do not necessarily cancel each other away. Instead, the correct relationship is that this has to contain A. And you just have to carefully reason this through, because f inverse of f of A are all points that get mapped to f of A. Well, A certainly gets mapped to f of A, but there might be some extra points that also do that for you. So at least it contains A. If f is like a bijection or something, then yeah, these will cancel each other away, and that's just equal to A. But in general, it will contain A. So f inverse of C is a closed set in X because you pulled it back, and it contains A. And it contains A. Also, P is a point in this closed set. Why? Because let's check it. F of P. So let's go back. So Q is in here. We must show that Q is in that set. And we said Q is equal to f of P, where P is in here. So P is an f inverse of C, because when you apply f of P, you get Q, right? You get Q. And actually, sorry about that. Yeah, sorry about that. Let me say it like this. So now recall that the closure of A, this is the smallest closed set in X, which contains A. Right? That's the smallest closed set. So this is a closed set. See, this is a closed set, and it contains A. So A closure, that's the smallest closed set that contains A. And this is some closed set in X which contains A. So what does that mean? So therefore, so you see what we did, we kind of have to go back to the beginning here. We picked a point Q, and we say Q is equal to f of P, and P is in the closure. Therefore, P is in f inverse of C. Since P is an A closure, and f inverse of C contains A. Okay, so let's say that again. P is an A closure. The reason why we know that is we said this all the way in the beginning. We probably forgot that fact, but we said that all the way in the beginning. Q is equal to F of P, where P is something in A closure. So P is an A closure, and F inverse of C is a closed set containing A. And A closure, that's the smallest closed set containing A. So if P belongs to this, right? I'm sorry, if P belongs to A closure, it's in every closed set that contains A. So this is a closed set that contains A. So by definition, P has to be here. And finally, so hence, that would mean that F of P is in C, right? We're just rewriting this condition. If P is in F inverse of C, it means F of P is in C, right? It's in C. And what is F of P? Well, F of P, that's just Q. So Q is in C. Is that what we wanted to show? Yes. We must show Q is in C. So this is the way the proof goes. This is actually not an easy proof, by the way. It's quite convoluted. There's nothing really clever that's being done in this proof. But, I mean, you can see there's nothing clever. We're just carefully using the definitions. But there's just so many things to unravel that it becomes fairly long. I think it's like one of the longest proofs we've done. But that's the way that it goes. I'm doing it mainly for the purposes of just practicing all of these definitions. You can see it proved in Moncrief's. I was curious to see how Moncrief's proves it, and he proves it in a totally different way. So if you want to look at his proof, you can look at his version. He uses a different definition for closure, which for the purposes of that proof is more convenient. So every definition that you use in topology has a positive and a negative. This version of closure is fairly complicated to use to prove what we want to prove. It works out in the end, but it's not like a few lines. It takes a bit more work. There's a different way of defining closure where the proof is much shorter. But then in other types of proofs, this version of closure is much easier to use, and the other variations in the definitions would be harder to. So no matter what definition you pick, some of them might be more useful to use in the proof than others. So because this is the definition we decided to use, you can see it's a bit longer than we wanted it to be in the end. So we have this. Now I wanted to mention another proposition. This one's actually very easy to prove. We'll put this on the homework problems. So this is the next proposition I wanted to mention. Let X be a topological space, and A is any subset with the subspace topology. This is what we talked about in the previous lecture. When you have a subset of a topological space, the topology that we always put on it is the subspace topology, unless we're doing something really bizarre, which I've never seen. It's always assumed to have the subspace topology. So then the inclusion mapping we call it I for the inclusion mapping. And this is the map that sends A into X by the rule that I of a point, let's call it X, get to X. It's almost like the identity mapping. In fact, you can say it's the identity mapping. The only difference is the identity mapping, the way you usually write it is a set is mapped to itself, whereas here it's mapped into X. So as a mapping from this space to that space, that's the inclusion mapping. So the inclusion mapping is a continuous mapping. So with the subspace topology, if you put some kind of random topology on this A, then it will not need to be a continuous mapping. But with the subspace topology, it's a continuous mapping. So you have to show that for any open set in X, if you take the inverse image of that open set, it's an open set in A with respect to the subspace topology. So this is an exercise problem we'll put on the homework. It's very easy to prove it. It's just a few lines. You can, of course, find it in Moncrief's if you're unsure how to do it, but that's the proposition I wanted to state. The other proposition that I wanted to state that you actually already had it on the homework. This is from the previous homework, so you already know it, but it's important. I want to write this again. So on the homework, you proved it with metric spaces, but the homework asked you to prove this result using open sets. And if you're proving it with open sets, then it's the exact same kind of proof that will work in any topological space. So you probably know where I'm going with this. It goes like this. So you would say that if X, Y, Z are topological spaces, and F and G are continuous maps between topological spaces, so then this composition as a mapping from X to Z is also continuous. So here's the picture that goes along with it. Here's X, here's Y, here's a mapping F, here's Z, here's a mapping G, and then you can follow the arrows. You go this way, then you go this way, and compositions, as you know, are written in this order for clear reasons, because you first apply, because when you write out the functions, this one sort of is on the inside, that's on the outside. So this is your composition. So you're saying if this is continuous, so we're saying that if this is continuous and this is continuous, we can conclude that that has to be continuous. So that part of the triangle has to be continuous. So this is from the homework. You already proven that. It works for arbitrary topological spaces. The simple reason for that is when you proved it on the homework using open sets, you specifically proved it using open sets, and so the argument generalizes to any topological space. So this is the proposition that we already know. Now, another proposition that I wanted to talk about continuous mappings is something that has to do with extending and contracting the domain and codomain. So let me say this. So this is extending, so this is restricting the domain and extending the codomain. So here's the way this goes. So proposition. So let's call this proposition 1. There's going to be two of them. Let X and Y be topological spaces, and F is a continuous map between them. Let A be a subset of X with the subspace topology. So then, this is the notation that we use. So this is the notation, maybe you've seen this before. This is restricted to A. This means you restrict F to a smaller subset. You restrict the domain of F to a smaller subset. So now it's a mapping from A to Y. How is this function defined? It's defined by the exact same rule. So if you pick an element of A, it gets mapped to the exact same element as this one does. The only difference between F and F restricted to A is that this one has a smaller domain, but the rule of the function where it maps a particular element remains the same. So then the restricted map is also continuous, which is not a surprise, right? So this one, proposition 1 is about restricting the domain because we're making the domain smaller. And the proof of this is actually a one-liner proof. Here's the picture. We have A going to X by the inclusion mapping, and then X goes to Y by the function, and then the restriction, this is F restricted to A. This one is continued. The inclusion is continuous, and the function is continuous by assumption. The inclusion is continuous, that's the earlier proposition, so therefore the composition, this composition, which is the restricted function from the smaller set, is also continuous. Okay, so this is proposition 1. It's a one-liner. In fact, there's not even any words here. It's just one nice picture that shows you how the whole thing fits together. So this is proposition 1. So this is about restricting the domain. Now I want to talk about the other one, which is very similar to it. This is about extending the codomain. So here's how this one goes. Let's call this proposition 2. Though probably giving these proposition names does not make a lot of sense because we're kind of writing down these propositions in some kind of random type of an ordering. This is maybe like the 6th proposition today or something. So here's how this goes. So let X and Y be topological spaces, and X is a function from X to Y is a continuous map. Let's remove this. And this one's going to go a little bit differently. Is a continuous map. And suppose Y is a subspace of a larger space. So when I say space, I mean a topological space. So Y is a subspace of a larger space Z. So there's a larger topological space, and the topology of Y is the subspace topology. Of course, it's always the subspace topology of some larger space. So then F is also a function from X to Z, right? This is, so as you know from a proof writing class, the X, this is called the domain. That's the domain of the function. That's the set, the input set of the function. This never changes. You're not allowed to change the domain. The moment you change the domain of the function, you have a different function. But this second object on the other side of the arrow, this is referred to as the codomain. That's not necessarily the range. The range is the set of all possible outputs. The codomain instead is the set where the elements are being mapped to. So this Y contains the output values. They're not necessarily equal to all of the output values, but it contains the output values. So the range will be contained in Y. So this is the, what you say, the codomain. So suppose Y is a subspace of a larger space. So then X. So then it's correct. You can always replace this by something larger, right? You can always make this something larger. So we're saying that if Y is a subspace of a larger space, so then F, when you think of it, because F is also a function from X to Z, so F as a function from X to Z between these two spaces is also continuous. Is also continuous. So you can prove this yourself. It's very simple. You can find it in Moncrief. It's just a few lines. But small little things like that need to be mentioned. Like in math, we're not just allowed to assume things without proving them. So even though these seem very silly, you do have to carefully mention them, because when we use them later on, we have justified them and we can use them. Now, I want to move to the definition of a homeomorphism. Let's discuss a homeomorphism. Because a homeomorphism, this is sort of like the fundamental idea of topology. So let us discuss homeomorphisms, or you can call them, I prefer to say isomorphisms. Isomorphisms. But then you should emphasize what type of isomorphism. So this is isomorphisms of topological spaces. The word isomorphism is overused in mathematics. So isomorphism in what sense? So sometimes things can be isomorphic as topological spaces, but not isomorphic as metric spaces. And I'll show you an example of that very soon. Whereas the word homeomorphism refers to topology. So there's no ambiguity of what we mean. So as we've said, morphism is some kind of transformation, and homeo means the same. So it's the same type of transformation. Intuitively, this is what we were saying earlier on our first lecture when we introduced some intuition into the class. This is what we were saying, that if you have a region that looks like this, you can imagine that you take this region, if it's made out of like a rubber sheet, you can just stretch out the rubber sheet until it turns into a disk. Okay, so you just pull it all in all directions until it turns into this. So topologically speaking, you would say this is the exact same space, because we do not care about distances or sizes or anything like that. You can just move it around, but it has to be done in a continuous way. What you're not allowed to do is you're not allowed to take this kind of object and then convert it into something like this, into two separate pieces, because that will require you to take a pair of scissors, cut this down the middle, and it gets separated. And that's no longer continuous, because if you have 2 points that are right next to each other, right on that place where you cut it, these 2 points are right next to each other. By cutting it down, these 2 points become separated. They become far away from each other. They're no longer close. So it's no longer a continuous mapping. So here is the formal definition of a homeomorphism. So definition. So let X and Y be topological spaces. So we say F from X to Y is a homeomorphism. Or if you want to say, sometimes I'll say an isomorphism. But you might have seen the word isomorphism in other classes before. Maybe in like a linear algebra class, you talk about isomorphic vector spaces. But there you talk about vector spaces. Here we're talking about topological spaces. But it's a similar idea, that is a homeomorphism when the following properties are satisfied. So the first property is F is a bijective mapping. It's a bijective mapping. This should make sense, right? There's a one-to-one correspondence, right? You're saying that one kind of space is being slightly deformed into another type of space. So every point, when it gets deformed to a different point, it's in a one-to-one way. It's not like different things go to the same point. So like, for example, maybe just to show you what I mean, you can, of course, take this disk and you can have a constant mapping which takes every point and maps it to the center. So everything is being mapped to the center. This is actually a continuous mapping because it's a constant mapping, but then you collapse everything down to a point, right? That's no longer a bijection. I think we can agree that these are not homeomorphic. You cannot twist this. All you're saying is you collapse it down to a point, which you could, but the spaces are not homeomorphic. So we actually want this to be a bijective mapping. Then the second thing is we want F is a continuous mapping. So bijective would mean this is one-to-one injective, so different elements of X get mapped to different elements in Y. And it's a surjection, or you also say onto, which means for anything in Y, you can find something in X that goes to it. And then the inverse map that goes the other way around, F inverse, that goes the other way around from Y to X, is also a continuous mapping. Now, some of you might be confused, and you might say, but is it not true that this one is automatically true? So this is a question you can ask. You can ask, does it not follow that 3 is automatically true from part 1 and part 2? So if the function is a bijection, it has an inverse function. So that's like part 1. And F is continuous. So is it not true that the inverse mapping is continuous? And the answer to this question is no. It does not have to. So I'm going to give you two examples of this. One of them is not going to be very interesting. It's going to be very silly. And then I'll give you a much more satisfying example afterwards that makes you appreciate. So the first example, it's more like a pathological type of example just to show you how things can go wrong. But when you see that example, you're going to say, but in practice, we never even deal with such spaces anyway. What about like nicer spaces that we generally come across, like more reasonable kind of spaces? So I'll show it to you with a more reasonable space as well. So I'll give you two examples of this. So let me kind of move this aside for now. That's the definition. We'll return back to it. So here's an example. So here X, let's say X is the set of integers. Does not matter. Let's say it's the set of integers with the discrete topology. So the discrete topology means every set in X. So by every set, we mean every subset in X is open. And Y is the set of integers again, but with the indiscrete topology. So the indiscrete topology is the opposite. So no set in Y is open, except for what you always must have, the two extreme examples, the empty set and Y itself, so the set of integers. So recall what we said. Indiscrete and discrete topologies are often good for trying to find counterexamples. And now we're going to define a function from X to Y. And the function is very simple. F of n. So these are just, if you wanted to, you can just write it's a function from the integers to the integers. But then that would be a little bit confusing because you're kind of using the same symbol, but there's different topologies. So that's why I prefer to use two different letters so you can distinguish them. You can, of course, write Z, comma, maybe like the discrete topology and Z, comma, I for the indiscrete topology, but that looks fairly complicated. So I'll just write it like this. So and you map an integer to itself. So the identity mapping, okay, this is n. So the identity mapping So be very careful. The identity mapping is always continuous, but in the so the identity mapping is always continuous when you're mapping the same space to itself. Here, it's the same set, but it's a different space. Right? The spaces are different. As a mapping between sets, it's the identity mapping, but the topologies are different. So that's why I say it's the identity mapping on sets. It's not the identity mapping on spaces. So these are two different spaces. But it is the identity mapping. You're just mapping an element to itself. So it's clearly a bijection and all of that. Now, this is continuous. Why is this continuous? So this map, this is clearly continuous, since if U is something that's open in Y, then U is either the empty set or U is the set of integers, because Y has the indiscrete topology. So we pick an open subset of Y, it's either the empty set or the set of integers. So F inverse of U, when you do the pullback, it will either be the empty set or the set of integers. Right, the pullback of that is the empty set. The pullback of the set of integers is the set of integers, because this is the identity mapping. And both of these are open, and these are open in X. Right? These are open in X because, well, the extreme sets are always open no matter what. But even furthermore, this has the discrete topology, so everything's open. So this is going to be open. So these are going to be open, but what about the other way around? So, but let's look at the inverse function. So then, the inverse function, this is going from y to x, and f of n is still n, because it's the identity map. I'm sorry, I meant to say f inverse of n is still n. Sorry about that. Yeah, so f inverse of n is still n. But let us check if the pullback of an open set is open. In other words, we want to check if this is continuous. Right? So this one is continuous, but let's check if this one is continuous. So we have to check if the pullback of an open set is open. So here's what you can do. So let U be equal to the set containing 1. Does not matter. This is an open set in X, because X has the discrete topology, so everything's open. You can pick whatever you want. Then F inverse. Now here's the thing. It's F inverse of U. That's the way you write it, because it's the pullback of F inverse. You see that? It's the pullback of F inverse. So you're pulling back, but you're pulling back F inverse. So it's F inverse, and it's the inverse of that. So you can say it's F of U, but it does not matter. It's the identity mapping. So this is just U, so it's just 1. And this is not open in Y, because Y has the indiscrete topology. The only things which are open are the empty set and the entire space. So F inverse from Y to X is not continuous. So in this example, you can see that the inverse function is not a continuous function, even though the original function was continuous and even though it was a bijection. But this example, not the most satisfying example. It looks very forced, very, very silly. You can say, well, maybe there's some more reasonable kind of spaces where this kind of strange behavior does not happen. So let me give you a more reasonable example, and then you can see even in like more reasonable types of examples, the inverse function does not need to be continuous. So let's look at this one. So here we're going to, so the ambient space is R2. So that's kind of, think of that as our universe. And actually, no. Let me, yeah, so the ambient space is going to be R2. So let me change this a little bit. So we're going to do this again later on, so it makes sense to introduce it now. So let me say this. Let C be the set of complex numbers. So the set of complex numbers, as we all know, this is the set of the form A plus BI, where A and B are real. And note, there is a bijection there is a bijection between the complex number and R2. So it's the obvious bijection, that if you have A plus BI, you map it to A comma B. So there's a bijection between them. So we can topologize. So we can topologize the complex plane by saying that U as a subset of the complex plane is open if and only if U corresponds to an open set in R2. So you're using the topology on R2 to put a topology on the complex numbers. An open subset of the complex numbers, if you like pair the real and imaginary parts into pairs, so that will give you the corresponding region in the plane. So as a region of the plane, if that corresponding region is an open subset, you declare that to be an open subset. It's sort of the most reasonable way to do it. In fact, how do we visualize the complex numbers? We visualize the complex numbers in exactly the same way we visualize as R2. Okay, so we have this. And so these are the complex numbers. And let S1, so let S1, this is going to be the unit circle in the complex numbers. So why do we write S1? So S stands for sphere. So this is sphere. And the 1 stands for dimension. Because a circle, it's kind of like a sphere, but a sphere is 2 dimensions and a circle is 1 dimension. So it's like a 1-dimensional sphere. So that's why we write S1. So this is the unit circle in the complex plane. So this is the unit circle. This is S1. The way you can write it is you can say that S1, so if you have a complex number Z, right, complex number Z, there's an angle that's being formed. So you can write this as cosine theta plus I sine theta. And then by Euler's identity, this would just be e to the I theta. Okay? So you have a complex number, and the absolute value of a complex number, that's the square root of x squared plus y squared, which in this case is equal to 1 because you're on the unit circle. So you can define S1 as the set of complex numbers with the property that the absolute value of z is equal to 1. So that's how you can define it. This will typically be the way we will work with the circle. It's more convenient to use complex notation when working with the unit circle. And later on in the semester, this is the way we would typically work with it. And of course, this unit circle, this comes equipped with the subspace topology, as the subspace topology. So this S1, it's a subset of C, and C is a topological space, so it has the subspace topology. So that's the unit circle. So now let's do this. Let me move this aside. So let X be the following interval. This is the interval that contains 0, and it goes up to 2 pi. Okay, so this is the real line. And on the real line, you have 0, you have 2 pi not being included, and then you have all of this. Okay, that's the interval. So this is X. And then Y is going to be the unit circle. So you have your complex plane, and within the complex plane, you have the unit circle. Okay, that's your unit circle. And you're going to define the following mapping, F. This is going to be F. So F is going to be a map from X to the unit circle. The picture here that you want to have in mind is what this mapping is doing is that it's going to take these 2 endpoints and is going to wrap them around in the circle. So it's almost as if you're gluing the 2 endpoints together. Now, the reason why we leave this one omitted is because we want this to be a 1-to-1 mapping. If these 2 points were both included, then both of these points get glued together and they get mapped to the same point on the circle. And we want to avoid that. We want this to be a one-to-one mapping. So that's why we exclude this endpoint. So we have a map from x to y, and it's going to be defined by the following rule. With the rule of this mapping is going to be this. So f of whatever input, you can call it x, you can call it theta, it does not matter. F of theta. So theta is an element in x, so it's going to be some number from 0 to 2 pi, and you're going to send it to by using Euler's identity, e to the I theta. That's the way it goes. It's kind of what we said over here. If you have a point on the unit circle, there's an angle, so x and y, the real and imaginary components, are the cosine and sine of the angle, and then you have Euler's identity, e to the I theta. So this is e to the I theta, and this is the mapping. And this mapping, and by the way, maybe we should emphasize that this point and this point, they get glued together. This is e to the 0, which is 1, and e to the 2 pi I is also 1. So they get glued right over here. So that's like the point where they both kind of get glued together. And we can visually see by using the open set version of continuity that this mapping is continuous. So how can we see that this is actually continuous? Well, intuitively, it makes sense, right? Intuitively, what are you doing? You're taking these two endpoints. Think of this as like a wire, a metal wire. You're taking these two metal endpoints. What is the function doing? It's bending the wire into a circle. So that's like a continuous way. You're not breaking the space. So it's continuous. So, but you can also see it with open sets. So is it true? So basically, we're asking this. So is it true that the pullback of an open set is an open set? Is it true that the pullback of an open set is an open set? So let's check this. So let's pick an open set on the circle. Now the circle has the subspace topology. It has the subspace topology. So how do you find? So let's just recall this. This is just good for practice. Open in Y has the form that it's open in C, and then you intersect it with Y. Right? That's the subspace topology. Something is open in Y if it's an open set in the ambient space, and then you intersect it with Y. So for example, if you were to draw this disk, you're going to intersect it, and you're only going to get that portion. So you're only going to get the intersection. So you're going to get this. You're going to get this with the open endpoints. Okay. So this is an open set contained in S1. Now, when you pull this back, how would that look like? Notice you're not touching this, right? You're not touching this. So you're staying away from that point so you're staying away from the endpoints. And then if you unravel it back, if you were to open this up again, right, you were to unravel it back, you would get an interval that would look something like this, right? You would get an interval that would look something like that. So this is an open subset of X. So you can see that if you pick an open set, and let's say you stay away from that point, you pick an open set, then the inverse image of that open set is an open set, right? But you may say, well, what if you have an open set and it contains that point? Do things go wrong? So actually, no, they do not. So here's the reason why not. So if you have an open set here, so let's suppose you have an open interval sort of wrapped around the circle. These are endpoints being included just to show it's an open interval. What's going to happen with this? Well, you're going to include this point, and then you're going to have a piece of your interval. So it's going to go like this. You're going to have this. You're going to have the piece of the interval, and then you're going to have the remaining piece of the interval on the other side. You're going to have the remaining piece of the interval over here. It's going to go like that. And you say, is this actually open? And the answer is yes, because you can draw. So for example, here's an open interval, and here's an open interval. Right? So here's two open intervals. Now, if you take, so this is an open interval in X, right? It's a union of two open intervals in X. If you take this open interval, right, the union of these two open intervals, and you intersect it with X, what kind of picture do you get? You get this piece and this piece. So this is actually an open subset of X. That's okay. That is an open subset of X. But what happens when you look at the inverse image? So when you look at the inverse image, you get a very different picture. So let's see what happens with the inverse image. I'm sorry, I kept on saying, I meant to say, let's see what happens with the inverse function. So now let's check what happens with the inverse function. So the inverse function will go from F inverse from Y to X. So that's the inverse function. So this time it goes in the opposite direction. It goes like this. Right? F inverse, it goes like this. So let's check. Let us check the continuity condition by seeing if the pullback of an open set is open. So now, when we take the pullback, we have to take the pullback in X. We have to take an open set in X because you see this is the inverse mapping. It goes from Y to X. So now we pick an open set in X. So let's draw an open interval in X and we stay away from the endpoints. So let's say we have something like this. Okay, so this is the open interval we have. Where did this open interval end up? The inverse image of this, well, it's going to get wrapped back to the circle and it's going to stay away from those points. So it's going to end up over here. So it's going to end up something, let's say, like this. So is this an open subset of the circle? It is, right? So if you pick an open interval and it stays away from these endpoints, then the inverse image of it, you see, it might be confusing. It's the inverse image of F inverse. So really, it's the forward image of it, right? So the pullback, right? So it's the inverse image of F inverse of the set, which is another way of saying the forward image of the original set, right? Because you're pulling back F inverse, or you're pushing forward the original set. So it goes here. And as you can see here, that's an open subset. Now problems begin to happen when you pick an open subset that includes the endpoint. So now let's see what happens there. If you include this endpoints, let's say something like this, that's an open subset, right? This is an open subset. The reason why this is an open subset of X is because here's an open interval, right? That's an open interval. This is an open interval of the real line. That's the open interval of the ambient space. This is the subspace topology. If you take this open set in the ambient space and you intersect it with X, you get this kind of a picture. So by definition, that's an open interval of X. But where does this end up in our picture? So in our picture, 0 gets mapped to 1, and then this piece will get wrapped around like that. So you would end up with this. That's what you end up with. And this is not open in S1. That's no longer open in S1. Because this point is being included. This is not an open subset of S1 anymore. Because there's no way to get a picture like that by intersecting with some kind of like larger disk or something. There's this larger open disk. It's not going to give you that closed off point. So this is not an open set. So this means that this function that we have over here, this is not continuous. It's not a continuous function. The inverse function is not continuous. So this is like a more satisfying kind of example because the spaces are a little bit more reasonable kind of spaces that we're used to. And intuitively, this should make sense because what is the inverse function doing? The inverse function is mapping the circle to this line by cutting it. So basically what you're doing is you're taking a pair of scissors, right? This is sort of like a pair of scissors or something, however you draw scissors. So you take a pair of scissors, you cut, right? That's basically what you're doing. You're taking a pair of scissors, you're cutting your space Y, and you're unraveling it into an open, I'm sorry, not into, but into an interval. You unravel it into an interval. And the problem occurs exactly where you cut it. At the place where you cut it, if that's the point where it's being cut, you're going to have a point on one side and you're going to have a point on the other side. And one of these points ends up over here and one of these points ends up over there. They end up on opposite sides. And that's the reason why it's not continuous, because 2 points that were close together become far apart after you apply the function. So you are destroying the space, right? So in this picture, you are destroying the space. You are destroying it. You're doing something that's not continuous, not a continuous operation. You're breaking the space apart. And so points get separated apart. That's the destroying process. So this space is being destroyed. So it's not continuous. So now we can kind of return back. Well, I took it down. So we can kind of return back to our definition. So going back to our definition that we had is we said f from x to y is a homeomorphism or an isomorphism of topological spaces if the three things happen. F is a bijection, F is continuous, and the third requirement is F inverse from y to x is also continuous. There's an alternative definition. So let me show you the alternative definition. There's another definition that you might see people say, and it goes like this. We actually already mentioned it in our examples. So the alternative definition is you would say you have a homeomorphism, f is a bijection, f is continuous, and you will replace this instead by saying f is open mapping, i.e. the push forward of an open set is open. And this is just because basically when you check that if you want to check that the inverse map is continuous, you have to take the inverse image of the inverse map applied to an open set. But then that's just another way of saying it's f of u. And then you have the push forward. So alternatively, you can say f is an open mapping, which means that if you take an open set in X and you push it forward, it gives you an open set. So this is like an alternative way to say that. So in some books, you see it written like this. I prefer to write it using inverse functions, but they're both equivalent to each other. I just wanted to show that to you so you're familiar with this alternative definition that is sometimes used. So now let me finish by giving you an example of a homeomorphism. So here's an example of a homeomorphism. So here's an example. The unit disk in R2, of course, R2 with the usual topology and the unit disk with the subspace topology. The unit disk in R2 is homeomorphic with R2. Okay, so we're saying this. Here's the unit disk. Let's call it D. And here's the entire plane, R2. And we're saying it's homeomorphic. Homeomorphic means there's a homeomorphism. We can find a homeomorphism that will map this disk to the entire plane. At first, it seems impossible because the disk is finite. It has finite amount of size, finite amount of area, and the plane has an infinite amount of area. But you have to get used to the fact that this is topology. Sizes do not matter. So this simply does not matter. And the way you can do this is, how do you come up with a homeomorphism? So here's the way you can do it. So let me draw the picture a little bit more carefully. I'm going to just draw a solid circle because it's easier to draw. So that's supposed to be the unit disk. And the unit disk is sitting inside the plane. And this is the way the function is going to be defined. So we want to define a bijection from the unit disk to the plane. We want to come up with a formula that will do it for us. So the way you would do this is you pick a point somewhere in the disk. So let's pick something other than the origin. So you pick a point, let's call it X. Okay? So what do you do? So here's the idea. The origin and X, they determine for you a vector. Right? There's this vector that's being created. And the idea is the closer you get to the boundary, the further you push this away. You kind of want things to blow up to the boundary because the plane, it goes out to infinity. So you want to basically go in that direction, and the closer you get to the boundary, things start to blow up. And then this way you kind of escape out to infinity. So the way this function is therefore going to be defined is like this. You're going to write, so for x in the unit disk, you would set f of x equal to, so you're going to do x. So it's going to basically be like this. It's going to be a constant times x. It's a scalar times x. So x is your vector. It points in a certain direction, and then you want to rescale it by a certain amount so that if you're close to the boundary of the circle, it escapes out to infinity, and this way you end up hitting every point in the plane. So the way you would do this is you want to going to rescale it in the following way. The constant, the rescaling constant, it's going to go like this. It would be 1 divided by 1 minus the norm of x. So let's say we're using here the Euclidean norm. This is the Euclidean distance, the sum of squares distance. This is the way you do it, because notice what happens. The closer x gets to the boundary, the norm of x, the Euclidean distance, becomes 1, right? And then you have 1 minus 1, that becomes 0. Okay, so the denominator becomes 0, and so it blows up. So you can also write it like this. So you can also say it's x, the vector x, divided by the scalar 1 minus the norm of x. Maybe you can even emphasize the 2 norm of x like this. So that's the function. So this is the function from here to here. So as an exercise, so this is going to be an exercise. intuitively, it should be clear. You're going to show F is a homeomorphism. Maybe you will have to use delta epsilon somewhere, because after all, these are metric spaces. They are topological spaces, but they're also metric spaces. So you can show its continuous map between metric spaces. So maybe you have to use a delta epsilon argument, but I think this should make it clear. It should be clear that this is a one-to-one mapping, because if you have a different value of x, if it's located on a different ray, then they get mapped to two different points on these blue lines. But what if this x is somewhere else on this on the same blue line? So if you have an x in the unit disk somewhere over here, then this x gets pushed further out. So one of them will get pushed further out than the other one, because this one's closer to the boundary. So again, they get mapped to different points. So the origin gets mapped to 0, of course, because this is the origin, so it's 0, 0 divided by, so the norm is going to be 0. So it's x, so it's the origin 0, 0 divided by 1. So that's going to be just 0. So the origin will not move, but everything else gets moved. And then it should be clear that different points in the disk end up at different points in the plane. And furthermore, every point in the plane can be gained in such a way. And why is this function continuous? Well, the simple reason, I mean, this is a very sloppy kind of an answer, but usually in calculus, when things are not continuous, it's when you have these piecewise conditions. It's when you have a function that's defined with many different types of conditions together. So here, since you can kind of write everything in just one single formula, that's an indication it's probably continuous. But of course, that's not a very convincing kind of a proof. So you might have to do a delta epsilon type of a proof to show it. So some work is actually required to show it's continuous. But I think it's a good exercise to show that a mapping is continuous. So this will conclude our discussion on continuous maps. And we'll continue next time. So today we finished by introducing this thing called homeomorphisms. This is when two topological spaces are treated as the same space. And then we'll continue next time talking about connected spaces.